All right, for our next talk, Daniel's going to stay up here, and he will be joined by co-founder and chief technical officer of Linguamatics, David Milward.
Okay, so I'll talk about the ChiKEL project, and that's involved both ChemAxon and Linguamatics. And on our side, it was mainly myself and Peter Corbett, and on ChemAxon's side, Daniel plus Timir and Nora. So I'll say a little bit about the project, talk about where we were starting from, and then talk about the first phase of the project, which is just coming to an end, which was the first year of a project, and then talk a little bit about what we're going to do next in the following year. So motivations, well, text mining's pretty well established in the drug discovery area for things like protein-protein interactions, the gene-disease associations, things like biomarkers, mutations. There's growing use in other areas, and there's a widening document sources, things like patents, which are being used more for scientific knowledge, as well as intellectual property and competitive intelligence. And we want to be able to combine the NLP-based text mining with the chemical search and visualization based on structure. So this is a 2-year project supported by the European Union. So where were we starting from? Well, for a couple of years, we've had an integration with the substructure and similarity search from ChemAxon. So you can take a SMILES representation, which you can draw, of course, in something like Marvin Sketch, and then you can look within your ontologies and find all the compounds which have that substructure. And with that kind of ability, it then means you can ask these questions like, for a particular substructure, what proteins are inhibited by compounds with that substructure. So we can take the substructure, we can then look in our document set, and then we can pick out various different components, various sentences which have the information such as imatinib, an inhibitor of BCR-ABL. So that gives us a construction, but we can also have other constructions such as it is a potent inhibitor of ABL, or we've got things like inhibition of ERBB2 signaling using lapatinib. So you've got various different syntactic constructions, but we can canonicalize them, put them in the appropriate columns, give them standardized identifiers, either in these cases preferred terms from an ontology, or the Hugo names for the genes. And we can also answer things like quantitative information, so we can look for things like IC50 values. We can look for example, in the text, where we might have something like an IC50 of 500 nanomolars or less. And also we can look inside the tables of the documents, depending a little bit on just how well they're structured, and always the structures as nicely as you might expect. But these are some examples of tables from the USPTO. So how's that currently achieved? Well, there's a wider set of tools than with a traditional search. So with the text mining engine, you're getting co-occurrence at different levels, whether it's at the document level, the paragraph level, the sentence, or going much more precisely, looking for things 1 or 2 words apart. You can also look for things with linguistic units between them. You can also look at the different regions of the structure, whether it's regions of the document, whether it's the abstracts or the methods, the description, for example. And then there's natural language processing, and that's trying to segment the text into meaningful units. So chunking it up so that you get units of text fitting together. And that gives you the ability then to have patterns which can determine the precise roles of the chemicals. So whether it's a product of a reaction or an inhibitor of an enzyme, for example. And then things like regular expression matching will find you your numerical information, your amounts, your dosages, your concentrations. You also, whereas a search engine is focused around finding the documents as the output, text mining is traditionally a little bit closer to the chemical searches in that you're coming up with more structured data as your output. So that can be lists of genes or diseases or compounds. It can be assertions where you're providing relationships. So it's rather more like providing, having a kind of flexible database, so you can have structured data, relationship output, tabular data. And you're providing these standardized IDs, and that means you can then connect to other data, connect to other databases, and make these indirect relationships going from database information and then joining that together with information from the literature. So just to show the limitations of where we were starting from, well, we were using a terminology, and we can plug in different terminologies, so things like KEBI from the EBI, or Joachim from the Erasmus Medical Center. And these kind of ontologies, I'll have a name of a compound, the various different synonyms that it might be expressed in, things like cyclosporin or CSA, neural, or a product code. And this will generally give pretty good results on things like Medline scientific articles. There aren't so many systematic names. If you have systematic names, these kind of ontologies will find the name, so recognize it will be a chemical name, but they're only going to understand parts of the name. So they'll understand the chloro part of the name. They might understand the I can't pronounce that one, the other parts of the name. So they'll find different components of the name, but they're not going to tend to get the whole name when it's a large systematic name. And that means that you're going to potentially miss those if your substructure search is crossing across those different components. So that's why we need the named structure, so we can pick up these novel compounds and deal properly with long systematic names. So the first phase of the project this first year has been to integrate the ChemAxon named structure, and that's integrating it so that we can find the exact position in the text and then do combinations of the text mining with the chemical search. So that's part of the work, and we've also done some investigation of clustering techniques to go into the next phase. So I'll now hand over to Daniel to describe this part.
Okay, so just a description of all the kind of names that we can looking for documents. So IUPAC names, so systematic names, and then the cast names, which are just a variant of systematic names, just the order of the parent and the substituent is different. Then you have common names, creatine, and drug names, generic proprietary abbreviations. So the aim is to capture as much as possible of those, so using dictionaries and algorithms. So the places where we can improve for name structure in general, and especially in the frame of this project, it's both conversion of systematic names and the dictionary names. And in documented structure, which is also used by I2E, is the error correction, dealing with all the things that you can get in a document, like punctuation, brackets, name that's split between two lines, or it's in a table. So there are lots of small details to deal with to be able to find the full name and as many names as possible. This is an interesting example that you have actually one word, and in the middle you have a dash. So amoxicillin resistant, and this is a name. This is just an English word, and this is something that we couldn't extract at the beginning of the project, but we realized that this is quite frequent, and it's very good that we actually can break this and find a name in this sentence. So here, this is an example from a document, I think from an article, and so this is the text, and then ideally what we want to find is all these names that appear, and you see that a lot of them are interesting problems because of the slash and these brackets and this the one I already spoke about. So this is one of the things that we improve by doing this this project, and the way that we want to drive the improvements is to make some evaluations. So we started with existing corpus, the SCAI corpus, which is some manual annotation on Medline abstracts. And to have bigger data, we also created new annotations on patents. And so we started with make some decisions, the guidelines about should we annotate polymers, should we annotate chemical elements, groups. So these are details, but we need to actually it sort of decides what we want to achieve or not, and also it's a question of harmonizing the data so that the measures are relevant and easily comparable. So that's something we have been doing to create these guidelines and then to use these guidelines to create the gold standard. And then as we continue the project, we start to evaluate the software against the gold standard, and obviously to do it as every version and continuously see the progresses, capture any regression that could happen. So we evaluate the quality, which means that we both try to have a high recall to find as many names as possible, but also the precision. So we don't want to think something is a name when it's not. So this evaluation is driving the development, and so we can see some preliminary results. So this is on a SCAI corpus, and so you have OSCAR 4 as a baseline of the existing tool, which is doing the recognition of names, and internally it's using opt-in for the conversion. And then we have different versions of ChemAxon. So during the life of this project, you can see this is the recall, and it's going up. You can see here that it's quite interesting to compare. So OSCAR converts significantly less names, but the precision is higher. So this is because actually it finds things. This is names where it can actually generate a structure, and so they are less than what you can get with ChemAxon. But actually, so this is the recall, the precision, and this is the F-score, which puts in one number both the precision and the recall. And you can see that, well, it's good, it's going up. But we will do more on this and also on the gold standard that we created. And I give back the floor to David.
Okay, so at the end of this first year, what we've managed to achieve with the integration is to have a substructure and similarity search, but now actually going over the various compounds found by the named structure. So we're creating the terminology, is then effectively created on the fly. We're getting together the different matches, and we can provide those with node IDs based on either smiles or inchi key. And then we're creating the preferred names using the structure to name. So, or the common name if that's available. So to give some examples, actually I don't know how clear that is on this screen. So here's some examples, and you can see the original names in the text on the right-hand side, and then we've had the name to structure, and then the structure to name to give standardized names on the left-hand side. So this is your resulting names, and that means that you're then going to be clustering together on the compounds which have the same structures. If you then want to sort of combine some of the text mining with the chemical search, you can look for a substructure, but then say, okay, well, actually, I only want substructures which are products of reactions, for example. So here we're using some of the linguistics to restrict it down so that we only have, for example, products. So we've got things like giving a certain amount of this particular compound. So we're looking in the sentence to give an indication of a role of the compounds in the particular patterns. So that's an advantage of having the precise location of the individual compounds so that we can then combine it with some fine-grained linguistic patterns. We've also started to investigate the clustering for the second phase of the project and looking at, for example, in this case, we're extracting chemical to disease associations from the documents using the text mining software, but then we're clustering the chemicals via maximal common substructure. So we can create heat maps and then see if we get any sort of particular clusters on the heat map, which suggests there's something interesting going on. So in the next phase of the project, we'll be continuing to provide further improvements to the named structure, working especially with our evaluation test sets. We'll be doing some integration of the chemical drawing and the chemical structures and results. But there's also there's a research package as well. So looking at integration of image recognition, things like OSRA, more automated clustering techniques, and looking at how we can look at Marcouche search integration, for example, if we import in the Thomson-Reuters Marcouche markup. I should say that some of these research packages, there's some scope for new work. So please do give us feedback and let us know any requirements you have, and we can try to fit that into the project. So, and here's the project address, ChiKEL@linguamatics.com. Thank you. So I'll just show up. So this is kind of some of the examples of the same one, the same output, but now exported into Excel using JChem for Excel so that you can actually sort of see the structures and see the where you're finding information from the actual document, from, in this case, looking for the products. Okay, thank you.